Hello, so recall that I solved this problem using the O of n space solution where I stored, all the left values or the max left values up until a certain point to an array and all the right values to an array. And then I computed the minimum value. I'm so tired. And because I'm so tired, I'm not going to be using my iPad, even though that may be easier. I just want to record on one place. That's going to be this laptop. So prepare again for the horrible drawings, and I'll try my best to make them good. Um, so this is the trapping rainwater problem. I don't think I'm gonna go too in depth. I don't know how to not go too in depth with the solution. I'm gonna assume my previous video has been watched. And following from that previous video, we'll use those same observations and mechanisms to actually solve this using the two-pointer approach. Also, I'm so tired. I should really stop yawning. Yawning in the video like this. Whatever, I'm all about authenticity on this channel, so sorry not sorry. Give an n non-negative integer representing an elevation map where the I have so much to do. I'm supposed to be grading student homework right now, but that can wait. God, I might just take a nap. I I might just take a nap and wake up at like 2. Anyway, given a non-negative integer representing an elevation map where the width of each bar is 1, compute how much water you can trap after raining. I'm going to assume you guys understand how this problem works, how they set this up, how they got this solution from the previous video. And now, so here is 0. Oh my god, I should just use my iPad to save my own self the time. So what do we have here? 0, 1, 0, 2, 1, 0, 1, 0, 2, 1, 0, 1, 3, 2, 1, 2, 1, 3, 2, 1, 2, 1. All right. And this is our height array, right? This elevation map that shows these black elevation boxes. And we're trying to calculate, how many 1 by 1 units of water can be stored between those elevation boxes and those heights. And, excuse me. Oh, I gotta sleep. This is so funny. Okay. Recall that previously we made two key observations. One being anything here on the boundary, um, sorry, anything here on the boundary is just going to overspill because there is nothing on the other side of it. Likewise over here, whatever is here is going to overspill. And we notice on the map here, so over here, everything here is going to overspill because there's no boundary on the right. And everything here is going to overspill because there's no boundary on the left. So we made the observation that for any body of water, right, where is it? For any body of water, such in this case, right, we had actually it's the other way. We had this block of size 1, we had a block of size 2, and then we had that body of water in between, right? And we said for any body of water here, we know that it's going to be stored between two elevations, right? And the amount of water you can store is going to be equal to the minimum elevation minus the here's 0, right? Minus the blocks or the elevation that's already in that position. So let me try to make this a bit more clean. So here's 0. And we said, okay, when I'm at this position, right, this position in my height array, corresponding here, size 0, I want to know how much water I can store in it. So you say, okay, take a look at my boundaries first. That's the first thing you do. And you say, I have this boundary of 1 and I have this boundary of 2. So what's the minimum water, or what's the max water that can be contained between these two boundaries without some overflow, right? So we know it's going to be equal to that minimum boundary of 1, right? Because here, if you store it between these two, the water will be trapped and contained. But if we try to store it to this maximum boundary of 2, well, there's going to be nothing over here to hold in that water, and that's going to overflow out, so it will not be trapped. Okay, so knowing that information, our calculation, at any point is min, right? We're going to take the minimum of two boundaries. So in this case, we took the minimum of boundary 1 and 2, and we are going to then subtract the current height of whatever boundary that you're at. So minus height at I, and in this case, if this is I, we're just going to minus height at I, and that's going to be minus 0, and we say that we can store 1 unit of water here. Now, I want you to pay attention to this computation of minus height at I, right? Minus height at I. So when I looked at other videos, today, after like finishing the problem, I realized not many people really go in depth with the explanation of this. And maybe I'm slow, but I think this is needed. So when we say minus height at I, right, we say, so let's pretend, how do I erase? Okay, I'm just not going to erase. Let's pretend we have some body of water here. That's size 1. Sorry, not body of water, the elevation height. And here's 2, right? And let's say we have something here that's size 1. All right? So you have this 1, 1, 2. There's no space between. And you want to know how much water can you store at this elevation position, right? So, of course, we do the same computation here, and this should make sense by now. You take the minimum of the left boundary and the right boundary, and we store that minimum. In this case, left is 1, and right is 2. We store that minimum, and this is going to be 1. And then we say, okay, that still doesn't tell me exactly how much water needed to store in this position. That tells me the max height I can potentially store in that position, but it doesn't tell me exactly if this height is even possible. So if here you have a boundary of 1, right? And let's say you just compute the minimum of 1 and 2, and you get 1, and you say, hey, this is perfect. I have a boundary, left boundary of 1, right boundary of 2, and I know that in here I can store 1 unit of water. Well, let's ask ourselves if this is correct. If we store 1 unit of water here, where there's already this elevated height of block 1, right, it's going to spill over down here because there's nothing on the left boundary to protect it. So even though we computed that this left height was minimum, was 1, right, and we said, okay, perfect, I can store 1 unit of water, we failed to do the check where the actual elevated height that we are currently at is also 1, meaning you actually can't store water here because if you store it on top of here, it's going to flow out and there's nothing here to contain it. So that's why we take minus height at I. So let's rewind and see what happens if we have that caveat or that case of minus height at I. Well, in this case, we get the minimum of the left boundary and the right boundary, and we say, okay, that's 1. I have the potential to store a maximum of 1 unit of water in this current position. So remember, we're at this position. But then we're going to ask, okay, I know I have the potential to store that water, but is it even possible if there's some elevated block that's either the same height as one of these or greater? Okay, so that's why we say, get the height of this. This is 1. And we're going to say, okay, subtract 1, minus 1. And that's going to give us 0. And that's going to tell us the actual amount of water that can be stored here. So I want to show you guys in this example that we did here, right? Let's erase this. Okay. This original example, right? We're taking a look at this 0 value here, right? So we have 0, 1, and 2. I kind of like this whiteboard, even though it's hard to draw, it's very simple. We have 0, 1, and 2. Sorry, we have 1, 0, 2, and we are currently at position 0, and we want to know, hey, at this place or at this potential elevation, how much water can be stored? And that's represented by this image here. So hopefully that makes sense. So we had 1, we have 0, and then we have 2. Since this array is the elevated heights, the elevated map. And in this case, you'll start with the same question, which is, what are my minimum left and right boundary, and is there even a minimum, is there a left boundary, and is there a right boundary to contain some water? This case, you get 1 as the minimum boundary. But then here, so unlike this case here, there's a difference. Here, we had an elevated height of 0, meaning there's actually nothing of this sort right here. So once we get the height, we say, okay, how much, I know that I have the potential to store a maximum of 1 unit of water here based on my boundaries, but now I need to know if that's actually possible. Well, if we go in this space, we see, oh yeah, there's nothing here. I can store that 1 unit of water here without any overflow because I know that water would be successfully trapped between these boundaries and it will not overflow. So you know that you can store 1 minus 0. See, this is 0. This height was 0. 1 minus 0, and that equals 1 body of water. You can count this as a unit. So I hope you guys would understand the case between this and this. And now hopefully you understand exactly why we minus height at I, right? Because even though when you calculate the minimum boundary, you have the potential, keyword potential, to store that amount of water in there, you still need to make sure that the elevated height is not too high, where even if you store that water, it's going to overflow out. All right, cool. Hopefully that makes sense. And now that we have this knowledge, I'm going to introduce a two-pointer approach. If you want to do the other approach that's much more straightforward, I recommend starting with that, which is what I did, where we stored the largest left boundary we've seen up until some point, and we store the largest right boundary that we've seen up until some point, and then we calculate the minimum as I just showed you, and we minus the height of that. Cool. So hopefully that makes sense, and I'll link that video in the description. All right. So how now can we use a two-pointer approach to have boundaries? Okay. So we knew a few key things, which is that I'm gonna type it here. I always want to know the tallest boundary I have seen on the left. I've seen on the left, and also the tallest boundary I have seen on the right. Whenever I'm at some point where I'm determining how much water to store. Okay, so when we're at 0 here, so what we're gonna do, I'm just gonna get straight into the approach. We're gonna have a low pointer that starts here, and we'll have, I'll call it right pointer that starts here. Okay, and we're gonna store in our variables the max left value and the max right value. So to start, we'll have max left equals 0, and we'll have max right value equals 1, because those are the boundaries that we see here. Okay, and what we're gonna do is this right pointer and this left pointer implicitly act as boundaries for each other, even though they're so far away, right? They still kind of act as each other's boundaries, because the check we're gonna do, we're gonna ask which of these is smaller, which max left and which max right value is smaller, right? In this case, it's 0. So you know that you can move this left pointer up by 1. And the reason we can do this is because we know that the right boundary is already bigger than the left boundary. This is saying that, okay, my right boundary, I have 1 here, and my left boundary, I have 0. And this right boundary, even though it's so far away, already acts as a right boundary to trap the water. Even though there are other boundaries in between this, we know that we only move this left pointer if it's less than the max right pointer. And if it's less than the max right pointer, that tells us this left, whatever's at the left value here, we moved it because it was smaller. And we know that that's our minimum value value of water that can be stored, because we only moved this because it was smaller. Okay? And, you're going to do the same computation where you take, the minimum. So what we did was we took the minimum of the left boundary and the right boundary, and we basically, and then we minus the height. I'm just going to say h at I. All right. In this case, if you're moving the left boundary, right, this tells you that the max left value was less than the max right value, less than or equal. Okay? And that means this is already implicitly computed, because the only reason you move this, the only reason you're in that like if branch, left is if max left is less than max right, then you're saying move this pointer, but now you can perform some computations, which is that you know what your minimum value is, or your max left value is, sorry, and you use that to just say max left minus height I, right? And this is if your max left is currently smaller than your right, right? You may ask, why can I use this right pointer as a right boundary, right? A valid right boundary, if maybe I'll see another bigger value like 3 here or 2 here later on that I haven't yet gotten to. Well, the way I like to think about it is these values, they don't even matter. Your right boundary is just there to tell you, can I even store this minimum of 1, right? Like, you can actually ignore everything in between here, and if left starts at 0 and right starts at 1, already you know my minimum like bottleneck is 0, which is here, which means I need to keep moving the left boundary to see if it somehow ever gets bigger than my right boundary, because at that point the right becomes the minimum in this computation that you take. This question is so hard to explain. I thought I could explain this very well, but explaining it out loud, I know I'm also confusing myself even more. But the idea, so let's see when we have 1 here. So when we have 1, these are the same, right? Left is at 1. And we know the reason that we moved left up was because it was the minimum boundary, right? Because it was less than right. That we have some if statement that's going to check if max left is less than max right. Okay? And now at this point, we just take the max left, which is just 1. We minus 1. So we take the max left, right? Minus height at I, which is 1, and we get 0. So we know we can't store any water in this position. And looking at the picture, that is the case. So if we keep going, right, we're not gonna, right now max left is 1 and max right is also 1. Now they're equal, so it doesn't matter which one we move, because right now we have this perfect contained boundary and we want to know the minimums or the maximums, so we can move. Let's just decide to move the left boundary over here. So now we'll get to 0 and max left is 1, right? So all we have to do again, we say right now max left, right now they're equal, so I don't care which one I move up, and we can see max left minus h at I is going to be 1 minus 0, and this tells us, it gives us 1, which means we can store a body of water here. And the reason we don't need to have anything like min of 1 and the right boundary here, so this is the right boundary, 1 and r, right now 1 is left, is because we already know if we're even checking or doing any computation with this left boundary, we moved it because it was less than the right boundary. And if it's less than the right boundary, then we already know that that's the minimum, if that makes sense. That's the minimum in this computation, because the minimum is determined by whichever pointer you move first, okay? And the other pointer that's still remaining acts as the boundary for that body of water, because you already have what was I gonna say? I don't even remember what I was gonna say. You already have something. I don't know. Anyway, I hope this kind of makes sense. Let's keep going. So then we get to 2, right? So, and then max left is still 1 and max right is 1, so it doesn't matter which one we move. So let's move left to 2, right? So we are at this block with 2 there. And max left so far, well, we're going to update it to whatever value we're on, and max left is going to become 2. And then we're going to get, and then since we moved it, we can assume that we moved it because it had a lower left boundary minimum than whatever was on the right. And we'll just do 2 minus the height at I, which is 2. which is going to give us 0. And now max left is 2. Okay, and now we've reached this point where this left boundary is greater than the right boundary. So now the minimum shifts to this right pointer because you're saying now this is the minimum value that I want to use in my computation because the minimum left and right is going to be currently now it's going to be whatever's on the right because that one is less. And really, you don't care what's on this side of the left value at all because you know the only reason you were able to move the right pointer is because somehow it was less than. It was the boundary elevation height was less than whatever was on the left that you've seen so far. And you can imagine that whatever on the left will act as like an implicit boundary. Okay, and then in this case, you would right, we're moving out here, move it up because right now max left is greater than the max right, and we want to target the minimum. And at this point, we say how much water can we store here? Well, again, max right is 1. Well, we'll just update the current max right to where we're at. So it's 2 minus 2, which equals 0. And let's look at the picture. We can see, yeah, we can't store any water here. And now the max left and right are equal. So let's just move the left to be 1 here. So we now have some block that's going to be like 1, like this. And we're trying to ask if we can store any water here. So we're going to take the max left we've seen so far, which is 2. And we're going to minus 1. And we'll get 1. Right? 1 is here. I actually just got a little bit confused in that, like, in this case, we know the left boundary. We oh, I'm dumb. I'm not dumb, but we know the left boundary is going to stay at the max. So this max left is what we're doing the computation. So even when we move left up here, we still have our max left stored. And we'll do 2 minus 1, which equals 1. That tells us we can store 1 body of water here. And I guess I was a little confused on how does this know for sure at this stage that there's a right boundary that is going to be minimum of 1. I guess I'm a little confused. So for here, right, we know our max left. We know that the only reason we move max left is because actually they were equal, right? Oh, because they were equal. They're both 2. So I know that it's either, oh, yeah, because the only reason we moved left is either because it was equal to right, and the max left and max right were both 2 in this case, or it was less than right. So I know that whatever this is going to be, it will be less than that right boundary or equal to the right boundary. Okay, that makes a lot of sense to me. Okay, and then you're going to keep doing it in this manner, and you're going to add up, all these water units that you find. And I'm too lazy to keep going. So I'm going to go try to code this and hope to God this works. So we have our units of water equals 0, and we're returning 0 units of water. And I'm going to store the max left value that I've seen so far. And starting out, I'll just make it equal to height at 0, which is just that first value in my array. Right, you can see here I started at 0, and here I started at 1. And so in max, let's say max left and max right equals height, and I'm going to say n minus 1. I'm going to create a variable, n equals to height dollar. Okay, so now we need our 2 pointers that will help us, go through these right and left boundaries until they overlap, and we know that we are done. Int low equals 0, high equals to n minus 1, while low is less than high. Okay, so what do you want to do, right? We have these 2-pointer. We have 1-pointer here and 1-pointer here. And right off the bat, we need to know which one is less, which one is that minimum value so that we can move it, right? We can move it and the value over here will still act as our right boundary for us. So while low is less than high, we can check, excuse me, if max left is less than, what time is it? Max left is less than max right, then what do we do here? I forgot. So if max left is less than max right, um, okay, we're gonna move our pointer forward to whatever's next, like right, and then we're gonna do the computation of potentially how many units of water can be stored, and the computation is only gonna involve the max left variable minus the height at I, because we know that the left side was smaller, it was a smaller boundary than our right boundary, so we should be good to go. So we are gonna do a low plus plus, all right, let's move to this value here, and then let's update our math.max for the max left value to be whatever we see right now. Max left equals math.max of current max left and this current value that we're on, right, at I. And if we do it in this manner, so in the other video, I showed you that we could get negative numbers and we had to do the ternary operator check. But if we do this at this stage, we update max left to be, whatever value is max up until where we are right now. So in this case, max started at 0, and now it's going to be 1, right? And you may be like, oh, well, we might make a mistake when we try to add 2 units of water. But the reality is, this will never be negative because if we're at this point, right, and max left gets updated to 1, we do the computation of max left minus height at I. So max left will be 1 minus 1, which is 0, which still tells us that 0 units of water can be stored here. Hopefully that makes sense. And this also would never be negative because we are updating max left to be math.max of whatever the max left was and the current value is. So you can imagine that if max left gets updated to whatever current value height at I that we're on, then when we go to calculate the units of water by doing um max left minus height at I, then it will be 0 and above, because if max left was successfully updated to height at I, then this would just be 0, telling us we can't have any units of water here. And if it wasn't updated, then this would be either, this would probably be a higher value, stay the same, so we get a positive value here. So there will be no negatives. Okay, cool. So that's if max left is less than max right. And if they're equal, we can say less than or equal, but I'd just rather do an else clause that says, okay, if max right is less than max left, right, less than or equal to max left, then we're going to move the right pointer downwards. It doesn't matter which pointer we move downwards. I minus minus. We're going to update the max right, the math.max of max right, and height at I. And we're going to, again, do the same, units of water plus equals max right minus. Sorry, this should be height at low, I think. Yeah, because that's the current height we'd be on. And there's not even an I in here. This is high. Max right minus height. And hopefully that's it. So once this while loop is complete, we can imagine that we went through, all of these things here, right and left, and we calculated the units of water at each step. And yeah, I think that's it. So then we return units of water. Let's run this thing. I'm tired. cannot find symbol. Oh, okay. And submit. Yes. And as you can see, it's the same runtime. Actually, in the other video, when I was saying it's not going to be faster with this approach, the idea is not for it to be faster. The idea is that with this approach, we save that extra memory space that we had in the first approach. But they're still running at the same speed, but memory-wise, this one is more optimized, and the solution is much more simple in the code. So, hopefully that made sense. Sorry for this crazy video. I'm so happy right now because I'm done with the two-pointer section, and I'm gonna about to move on to the fast and slow pointers. But first, I have to go grade like 20 assignments. I'm tired. Pray for me. Goodbye.